And finally, I'm going to be talking about very briefly about RNN trackers. Actually, this title should have been under CNN plus RNN models, but initially I thought I was going to just do more stuff on this, then things changed, so just don't care about it. But at least I'm going to be talking about them. So what is a tracker? Well, the definition of a tracker is a bit ambiguous in many ways, because when you're tracking a visual target, it's obvious, but you may be tracking some part of a signal as well. So if you want to make its general definition, in general, it's a sequence-to-sequence problem. So in usually one dimension, which is the time dimension, you have a signal change, and you are trying to track a part of this signal. So when you're tracking that part of the signal, what you obtain is also a signal in time. If usually, when we say tracking, there is this dimension of time, which is a location of the signal. So it is like the signal as a sequence of time, most of the cases, and the output being a location as a function of time, which makes it a natural sequence-to-sequence problem. And in visual trackers, this problem is you're given a set of images, which is presumably a video, one scene, and the output is the pixel location of a tracked target or multiple targets. Before deep learning and recurrent neural networks, not before recurrent neural networks, before recurrent neural networks and deep learning became the de facto standard in every AI-based problem, people have been working on tracking, again, in 90s or 2000s, the first decade of this century. And they were doing some handcrafted stuff. They were using some models, and they were using some appearance by models, and they were trying to match, the problem was to match frame 1 to frame 2. I've worked on this problem a lot. I mean, one of you guys is actually, he's not here, but when I was in Aselsan, I was a part of a group who worked on target trackers in infrared images. So, and they are still doing it using the methods of the pre-deep learning era. So I'm pretty well familiar with that era. And in that era, the main problems of tracking were occlusion. So what happens when the target you're tracking is occluded behind something? So you're tracking something and it goes behind a tree. So what happens? Most of the time it gets destroyed. Because in these handcrafted models, the semantic idea that the object is behind a tree is so high level. And the tracking models those handcrafted models you've used, those algorithms, were usually signal-based and handcrafted basic models. You were given a template of the target. You were trying to find that target. And when it was behind that, occluded somewhere, you couldn't know it. So it's going to go behind that target or behind those. So if it's a human, you don't know that, you know that it's not going to fly, most probably. It is not a superhuman character. So you have some strategies in your head. And these strategies, these high-level strategies are learned. Most of the time, any of these challenges, occlusion or drifting is one of those. So you have a template, you're matching the target, but the target changes as you track it because it's moving. So you're seeing the target from one direction, then you start to see it from another direction. So the appearance model of the target changes. As it changes, if your model cannot update properly, well, you don't recognize the target anymore. And that black box, the definition of the tracking as you see it on the screen, drifts from on top of the target to somewhere. That was the main problem of tracking, because you did not define that target at a high level, semantic level, like deep learning does. Because in deep learning, convolutional networks define it as a car, regardless of the perspective of the car you're looking at it. However, in signal-based models, you have a template of the car from one direction, and if you look at it from another direction, those template matching algorithms did not work. So these were the main problems. So we were trying to associate. So when you associate multiple targets, you needed more strategies. And you applied things like probabilistic data association and etc. These are some titles which exceeds the context of this course. But if you know something about tracking, you know what probabilistic data association is. And mainly the appearance change, because you had an appearance model. And there were other problems as well. I found this on the internet. So these were the main problems of tracking. So similar appearance targets. That was another problem as well. So you're checking a car, white car. If there's another white car, in the old models, if you just come across that white car, it could just jump to the other one. Or when the camera moves, because you don't know what creates the motion is a camera. You always had to handcraftedly model all these effects in your target with recurrent neural networks and with deep learning, with deep recurrent neural networks and with deep convolutional recurrent neural networks, CNN plus RNNs. We could get rid of these because CNNs could carry any target of the scene to a higher level representation. So regardless of the point that you're looking at it, since you are trained with millions of images, it is there as a concept. You could track the concept. And while you're tracking the concept, you could learn those behavioral high-level concepts like, is it going behind a tree? Is it going to come back? If it comes back, where is it going to come back? If there's a tree, it's going to come back from the other side. These kind of things you could learn with a recurrent model because any of those high-level concepts can be defined as states of action in a scene. And regarding understanding states of actions or modeling state change in a historical way of events, LSTMs and recurrent models are perfect. So quickly, all those tracking models have been replaced within the last 5 years with deep convolutional and recurrent neural networks. And actually, most of the networks were based on some very well-known architectures that we have learned in convolutional networks and recurrent neural networks. So that was the reason I kind of just wanted the tracker-based things to be left to the end of the both courses, because when you know both convolutional networks and recurrent neural networks, it all makes sense to use them in trackers, because that's, if you know the usage of, if you know how to use convolutional or recurrent neural networks, there's designing a tracker which doesn't use them, it's meaningless. Okay, I'm going to show you some stuff, some very well-known techniques, how to apply them, and you'll have an idea. So it's another example to show you how difficult this training is. As you can see, it's impossible here. Occlusions and tracking this. What we do is basically, so before that, what we do, so conventionally what was done was, what is tracking is, you create an appearance model for the tracking track target. You have a model, you update the model in each frame and try to find it. Okay, and they were transparent models which you can understand. There were nothing non-transparent like weights or stuff. It was all handcrafted. So if you've handled some situation, like if it goes like out behind the tree, you can handcraft an algorithm to handle it. For another algorithm, it failed. But if you have enough scenarios in your training set with recurrent neural networks and deep learning, this problem was solved. How? RNN's ability to model sequences had a potential to solve this. And just like I told you, in the last decade, actually in the last 5 years, many CNN plus RNN models were proposed. I'm going to just visit some of them. So this is a very brief, how can I put it, infograph for what tracking is. You have the object, you have a presentation, you have a representation for the object, you detect those objects, that's how you do in your head. You assign identities to them. So this is like the first, this is like the second one, this is like the third one. So actually you're creating a sequence in your head, sequence of people with their appearance models. Then you track them. This very much looks like a sequence to sequence CNN plus RNN problem. So it looks like a video to image captioning problem. You can actually you can use encoders and decoders, and people have used it. I'm going to show you. Okay, so one of them is this is the very first idea. First you can think of. I mean, this is the most basic thing you can think of. It is one of the earliest, by the way, and it's from somewhere China, yes, and plus Belfast. It's a collaboration. They adopted LSTMs to CNN features they obtained from an image. And the idea was simple, guys. It's going to make a lot of sense to you. There are 2 lines here, 2 rows. Just ignore the second row now. Just look at the first row. You have a frame. you have a template, the first template of the image. It is like before the first frame, I'm telling you, track this, because that's usually the application of trackers. So in military, the ones that we have tracked, the pilot just shot, I mean, did not shoot with a gun, just pointed somewhere, some region, I'm going to track this. So you have a template of the target. So you're given the target, you apply a similarity learning function. It's a learned layer. It provides a proposal of images. So it kind of rigid proposal network, just like the RCNN of the object detectors from convolutional neural network. So it provides a proposal of patches. So this is selected proposal regions. You feed them to a convolutional layer, and they're being fed to the LSTM. And it says one of them is selected. Very simple idea. But the nice thing is the similarity function evolves at each frame, and the hidden states of the LSTM is kept for the next frame. So on the next frame, when you feed it, the similarity function, which evolved from the previous one, so it is like this temp, the first template is like the first hidden state. The next, the evolved one, because this template was searched in the frame and it evolved somehow. There's a mechanism here. You can check the paper. So it's like a hidden state fed to these models, and new proposals, and this hidden state fed to here. So it kind of handles the appearance model changes. This LSTM kind of handles the background versus appearance model interaction. And it worked perfect. And just much better than the previous ones. There was less drift. The challenges were much more solved. And people started to come up with very nice architectures, actually.
Hocam bir soru sorabilir miyim?
Please, but I cannot hear you.
Şimdi CNN'den çıkıp LSTM'e geliyor ya.
Hı-hı.
Yani burada convolution layer'dan elde ettiği feature vektörleri aslında LSTM'e aktarıp LSTM de onları hani memory cell'lerinde tutup ona göre de bir detection yapıyor aslında.
It's not doing a detection, but it's doing like a classification. It's trying to select which one of the sequence of proposals, because the number of proposals may vary. So this is a varying length sequence. So which one is the best? You select one of them. So it's making like a classification, not a detection.
Okay. Bir de şunu
But it's for this model. For the role you're about to propose, it is a detection.
Bir de şunu soracağım. Biraz embedded tarafa girebilir. Normalde hani biz bu CNN yapısını hani GPU tabanlı genellikle hani çalışıyoruz. Daha önce de size sorduğumda RNN, LSTM genellikle hani sequential bir yapı olduğu için CPU mantığında çalışıyor. Peki biz burada embedded tarafta bir multi-process görev paylaşımı yapabilir miyiz?
Well, very good question.
CNN tarafında GPU, LSTM tarafında CPU'yu devreye sokup orada bir sistem yapabilir miyiz, uygulayabilir miyiz?
Very good question. I'm going to translate the question to English because I've got some subscribers from the world, and this is a very good question. Your friend is asking, well, we've always we always said that when we were discussing previously, CNNs can be easily applied to GPUs and parallelized for GPUs and FPGAs, whatever. But for LSTMs, since we are just feeding the sequence one by one, well, the parallelization is a bit tricky. However, that's not the case for a tracker, because the tracker is real-time data. So if you can handle whatever you're doing in a single frame within a given limited time, so if you can guarantee a worst-case latency, which is the definition of real-time, by the way, then there is no problem. So for the question you're asking, you can definitely use the parallelization for this step. You can definitely use the parallelization for the convolutional layer as well. So for the LSTM layers, there could be multiple, because they've got multiple LSTMs. If your network, because an LSTM is a very simple architecture, you just do some kind of calculations, right? If you can do it within one frame length, which is if you're just tracking a video of 100 frames per second, your frame length is 10 milliseconds, okay? I guess Fred understood, but I'm trying to make everybody understand. And if you can fit all these steps in 10 milliseconds, well, then you're done. So about tracking real time, it is always fitting your job in a single frame length. Is this answer okay for you? Because even though you finish it earlier, the next frame will not arrive until the frame length is done. But this is not the case for, for a language translation. When you're translating a language, you are given a sentence. You can do it as fast as you can. However, in tracking, you have to wait for the next frame. So all you have to do is, you have to fit your single frame job in a single frame length. Fred, I think this was an answer. Don't you agree?
And I have one question again.
Okay, please.
Bu an diyeceğim hani biraz daha çok embedded tarafına geliyor gene. Hani embedded deep learning dersindeki quantization yöntemlerinde şimdi benim merak ettiğim burada CNN tarafında uyguladığımız atıyorum integer 8 quantization'dan elde ettiğimiz feature vektörleri direkt LSTM'e aktarmamız mı daha mantıklı? Yoksa LSTM layer'da ayrı bir quantization uygulayabilir miyiz?
Another very good question. I'm going to translate this one as well. Your friend is asking, okay, we are done with the framework, but he's asking what kind of embedded-based optimizations we can do, such as actuation quantizations and etc. Well, you can always quantize the actuations after training, which is called the post-training quantization, as you remember from 545, just like you said. So when you do that, you will have to quantize the actuations of this layer. You'll have to quantize the actuations of these layers. And you will have to quantize the actuations inside the LSTM as well. Because in LSTM, we have many gates. They all have actuations, multiplications there. You have to quantize them as well. And when you do that, whatever level quantization you're doing, 8-bit, 12-bit, or 4-bit, I don't know, you have to check your accuracies. Is your tracker still working fine? That's the first thing you do. So you come up to a point, you say, okay, when I just change the actuations from 32 bits, which is the single, or 16-bit, which is the single precision, to, for example, 8 bits, I still have very good accuracies in tracking. Then you're fine. If you want to do it better, more, if you want to apply more quantization, like 4 bits or 2 bits, then the same rule applies. You have to just apply a quantization-aware training for the entire network. So you'll do your training, including this layer, or the convolution layer, or the LSTM layers, using some quantization-aware techniques, just like we have spoken on the embedded deep learning course, 545.
Accuracy dışında hocam başka nelere etki edebilir mesela? Accuracy dışında.
Well, the only output of this system is accuracy. So I cannot think of anything else that it could affect. So if you just tweak the numbers a bit, the accuracy falls. What else? Our hearts can be broken. I think it's only the accuracy.
Yes. Well.
Okay, it's still good. Nothing else. Because that's the only thing we care about. This guy doesn't have any output. It provides a location of the target. If the location is true, it's high accuracy. If the location is bad, low accuracy. Nothing, there's no other output. Okay? Okay, very good questions, by the way, very advanced. Your friend is trying to just combine all 3 courses together: convolutional networks, recurrent networks, and embedded deep learning. All the courses that I give.
Aslında hocam bağlantılı sayılır hemen. Yani ufuk açıyor biraz daha çok. Çünkü tüm dersleri birbirine bağlı.
Yes, you're exactly right. Okay, another good idea. I regret that I've missed this because when we are talking about the variants of LSTMs, there's this convolutional LSTMs, which is like a convolutional layer, but with history. And actually, one of you have proposed a project for that. Which one of you? Let me remember. Kartal, it's you. You are going to use convolutional-based LSTMs for video processing, right?
Yep.
Okay. When I finish, I'm going to have some questions to you as well. What about data?
Okay.
The data, what you do. So this is very nice, guys. It is recurrent filter. So you know what the convolutional filter does? It provides some, what does convolutional filter does? In a deep layer, it detects trees. What if the appearance behavior of that tree is changing? then you have a filter which is recurrent and which is history that adapts and changes. And that is the very definition of a appearance model of a tracked target. So they come up with this conv LSTM, which is a filter LSTM. And the LSTM, in time, as new data comes, just learns and changes the filter. So it's about finding the right filter for the tracked target. And they have a fantastic mechanism for it, for the tracker. I'm going to go over the mechanism for you guys. This is the frame, new frame, guys, okay? Also, this is the template. So this is the target to be tracked. For the first frame, it was given by the operator, or for any frame, it is borrowed from the previous image, because the output of the tracker from the previous image was a region, which was presumably the target. So this is the target. You apply a CNN. So you've got a CNN here. So at this point, you have a 6x6 file, 256 filters. So you have a coarse, very large filter, so with very large depth. You apply this to a conv LSTM. So this conv LSTM is like another convolutional filter, which will change with each given frame. So it is like, as this guy changes, this thing evolves. I mean, it's a fantastic idea, and it makes a lot of sense. And at the output, there's a self state and hidden state. They are going to be fed to the next sequence, the next frame. We are just sending them there, so they are being sent here. At the output, this guy provides me a filter, and that filter will give me the place of the target. So it is like a magical filter. When you just convolve it on some given signal, it gives you the position of the target. The largest value is the position of the target. So as you can see, I'm going to convolve with something. This is convolution, something. So this is red region is the place of the target. That's the idea. That's the location, guys, the response map. So what am I convolving it with? This is the searched image, a CNN. At this point, I have a higher representation of the image. So for this higher representation, this conv LSTM is giving me a filter which would find the evolved appearance of the target in a response map. Fantastic, simple, and fantastic idea. This is one of the simplest trackers, single target trackers that I like most, conv LSTM based. Any questions about conv LSTM?
I have a question.
Please.
So we have two different, we have ECNN and STNN. Are there any differences between them?
But they are different CNNs and they are being learned, but they are CNNs. So this one gets the target image to be fed to the conv LSTM. So it is like this representation here, the output of the eCNN. It's the name of the CNN, so it's not a different type of CNN. It is a CNN. Its name is
It's
eCNN.
like a difference in notation. But
it's not like it's its name.
Mm-hmm.
But they have different parameters, as you know, because this is taking the whole image. This is taking a small region of the image, right?
Yes. Mm-hmm. Okay.
So it's feeding the conv LSTM. Conv LSTM is the LSTM that evolves the appearance model, and it provides a filter. We convolve it. We find the position of the target. Very nice idea, in my opinion. Recurrent filter. Okay, again, China. Hong Kong is now China. Okay, and another one. This time not visual, guys. And this time, it's multiple target tracking. Guys, multiple target tracking is another idea. I mean, I don't have time to get into the details of multiple target trackers. Multiple target trackers is because in multiple targets, when you have multiple targets, you have a possibility of just getting mixed between two appearances, right? When you're tracking some targets in a radar, this is the case. Or it could be a visual pedestrian target detection. That's what you do. So you have to just differentiate between them. So in this case, it is radar. Radar is like you are getting some readings, from an angle, and it changes. And from each angle, you are getting a signal value. Okay? So this angle, a signal value, this angle, a signal value, this angle, a signal value. First you do some pre-processing, okay? You are getting if the signal to noise ratio is higher than a value, which means there's a target there. So at this angle, I have a target. At this angle, I have 2 targets. At this angle, I have 3 targets. I have some 2 targets. And there could be problems with the signal as well. Maybe there was some interference to the radio signal that radar gets, and you couldn't detect it for a moment. And it's turning. So for some cases you can detect it, for some cases you cannot detect it. So there's a sequence of azimuth angles and distances, because it can calculate distances as well, because there are multiple radars. I don't know if you know how radars work, but simply it makes a triangulation. You have two radars and just change there. So if then they got signals, but there are multiple signals, and when you triangulate them, you can triangulate them wrong if you associate them wrong. So you've got inputs, and these are the ground truths, guys, that you feed to the loss function. You feed it to an LSTM model. So when you feed it to an LSTM model, you're actually feeding a number of detected targets, target candidates. These could be noise, or this could be the length of the input could be varying, because maybe you just detected a type of noise as the target, or the opposite, you have missed the target. So they could vary. We have a recurrent-based model in between, which is the BLSTM for this paper, which handles that situation. It says, well, this doesn't look like, in my history, there was no signal like that, so I'm just omitting this signal, it's noise. Or it says, there should have been a signal here, I'm just putting a signal here, outputting a signal here, and it can create dependencies within them. So this is a kind of multiple target tracker, which could fill in that association detail using the recurrent neural network. And we have this idea a lot, guys. Another more complicated version is about RNN-based trackers is, you have this. This is a bit more complex one. It's for pedestrian detection. So you've got a video sequence. You have from different frames, you have many targets detected. The first thing it does is, for re-identification, to map them, it creates a graph architecture. It's a bit strange paper, that's why it took my attention. In the graph architecture, every detection is a node. Every detection from each frame is a node. So for the 3 consecutive frames, each detection is represented in that graph. And in that graph, the edges have some values, which is like distances. And those distances are being calculated using an appearance model and using an optimization technique, which is the Kernighan-Lin optimizer. It is like, after the Kernighan-Lin optimizer, this guy creates a graph where each node is a detection between the frames. And if the 2 edges of different frames, so this green frame has a connection to this yellow frame, the yellow one is frame 1, so the green one is frame 0, kind of. So this guy has a distance and this guy has a distance. If the distance is small, they are matched. According to these matches, you create a sequence. The match could be correct, the match could be wrong. We have a matches. And they are being fed to a encoder-decoder model. The input of the encoder-decoder model is those matches. So the position of the first, the position, X, Y position, location of the first, the width of the, because they are just, you see, they are just rectangles around the pedestrian, the people, the width of it, the height of it, the second one. And at the output, we have the actual values where it should be. So the encoder-decoder handles those occlusions or kind of things that happens in a multiple tracking. So RNN-based trackers with more sophisticated architectures do handle not only single trackers, but multiple tracker problems, including association and tracking together, guys. So those are some nice examples of those. So before I finished, I'm going to show you something, because I realized that I forgot it, but it is Fırat's project. Fırat, I'm show you this.
Hocam, her nodu tespit etmesi accuracy etkileyen bir durum değil mi aslında?
Exactly, it is. If you try to detect every node, the LSTM will be flooded. That's why they have that graph mechanism to make good assumptions. So they provide some clever assumptions to the LSTM, which make it work better. Exactly. That's why they had it. Or they would have just fed the raw detection outputs to the LSTM, which most probably did not work for 40 people tracking. So answer to your question? Because that's what exactly you are asking, right? Exactly. That's why they have this mechanism. They have some kind of association mechanism which is not working perfect, but it is doing the job for the BLSTM easier. Right? Good. So, and this one, is it yours? Oh, it's not yours, I'm sorry. This is Kartal's. I'm going to find it.
Ben hocam ayrı bir doküman oluşturmuştum.
Bir yerdir ya. Çok
Yani makale yollamaktan ziyade.
And this one, yes. Yes. So, and this is what Fırat is trying, just wants to do. Let me just make it bigger. So this is the Rollo, guys. Do you remember YOLO? YOLO was the de facto object detector, guys. And it was a very nice architecture because before YOLO, object detection, if you remember this is from convolutional neural networks. People, in order to detect multiple objects in a scene, they have extracted different regions and just worked on different regions one by one. But YOLO, you look at once, was an idea which made the detection all at once in a parallel manner, so it worked very fast. And this is the recurrent YOLO. Recurrent YOLO is very simple. You feed the image or image sequence, so images one by one, frames one by one, to YOLO. And at the end of the YOLO, where you detect the objects, you just get that part out and just throw it away. You feed that high-level features, which is like features to be detected for the detection operation, and you feed it to an LSTM. So it is like this is doing a first detect, then track operation in an LSTM. That's why, since it's obtained from YOLO, it's called recurrent YOLO, which is Rollo. And this is one of the very famous ones because it does detection by tracking using YOLO and an LSTM. And that's a very nice idea as well. I forgot, maybe just I should have it in my slides, but thank you, Fred. So he's planning to use this in his project. So let me just make it bigger. And this is one of them. Okay. So I think this is all about, I would say, about trackers as well. But these are all very big, titles. There are a lot of things to find. I've provided some suggested reading as well. Anyways, this is all I'm going to say. Any questions?
Hocam ben projeye bakış açınızı merak ediyorum.